So now let's consider some specific examples in which we'll try to work out what the space-time interval is and what exactly it physically tells us. So let's consider a frame S prime, and in this frame S prime, let's consider a particular space-time point x1 prime, x2 prime, y2 prime, sorry, x1 prime, y1 prime, z1 prime. And let's consider a clock here, and the clock shows a time of t1 prime. And now let's consider the same spatial point, but at a future instant of time. That is, let's consider the future instant of time t2 prime, but at the same spatial location. So now let's consider the spacetime interval between these two spacetime points. So the spacetime interval between these two spacetime points is t2 prime minus t1 prime square times c square. And since the spatial parts are the same, the rest of the expression for the spacetime interval would be 0. So in this case, you can clearly see that the spacetime interval is positive. And so if we use our definition of c square d tau square, c square tau square, delta tau square, or delta tau prime square, let's just use delta tau. So c square delta tau square is this quantity. So what does this tell us? Well, it tells us that in this case, delta tau is just t2 prime minus t1 prime. So in other words, the space-time interval in this case corresponds to the time elapsed, or the time interval measured on a static clock in frame S prime. Okay, that is, there's a clock sitting at this spatial location, x1 prime, y1 prime, z1 prime, and the location doesn't change as seen by observer S prime, but the time interval that has elapsed on it has changed. And delta tau is a measure of that change. Okay, so delta tau, or c square delta tau square, is what we call the proper time interval. Okay, so this is called a proper time interval. So delta tau is what we call the proper time, is delta tau. And we've already seen that this quantity delta tau is a relativistic invariant. Okay, that is, all observers, all inertial observers will agree on the value of delta tau, provided that they construct delta tau using their the measure of a space-time interval in their coordinate system. So now let's consider an observer S. For example, observer S is a platform, okay, which is waiting for a train, and observer S prime is corresponds to these train observers, and there is a static clock on the train. So let's say this is the clock that's moving with an observer O prime Prakash on the train. Now we consider two space-time points. That is the location where O prime Prakash is in front of some observer O on the platform, and another space-time point where observer O prime Prakash is at the location of another observer A on the platform. And we look at the time interval that has elapsed on O prime's clock, and that time interval would be delta tau. Now, if observer S wants to construct the time interval delta tau, what they would do is they would first locate the space-time point where O and O prime meet, and they would label that point. So they would say that this is the point T1, X1, Y1, Z1. They would locate where observer O prime meets observer A prime, and they would say that that instant in time is T2, X2, Y2, and Z2. So note something important. The times that you're measuring are measured on different clocks. They're according to observer S, they are measured at the location of O's clock and at the location of A's clock. Okay, so this is not a clock that's at a single spatial position, it's a clock that's at a different spatial position. So in other words, T1 and T2 are different, but also X1 and X2 are different. And now what observer S needs to do is construct the quantity c square T2 square minus T1 square minus X2 minus X1 square minus Y2 minus Y1 square minus Z2 minus Z1 square. And they are guaranteed by the transformations of special relativity that once they construct this quantity, they will exactly get c square delta tau square, which is the proper time that has elapsed on O prime's clock. Now let's consider another possible construction of a space-time interval. So let's consider a frame S prime, and in that frame S prime, let's imagine that you have a rod placed like this, and you measure the ends of the rod simultaneously. That is, at a time t1 prime, you measure one end of the rod, and at the same instant of time, you measure the other end of the rod. And let's suppose that this rod is placed along the x-axis. So the y-coordinate would be unchanged. Then x2 prime minus x1 prime would just give the length of the rod. Okay, and let's assume that this rod is at rest in the frame S prime. Now, if you ask what is the space-time interval between these two space-time points, what you would get is t1 prime. So since we can construct this the space-time interval by taking this difference minus x2 prime minus x1 prime square minus, oops, the y coordinates and the z coordinates have not changed, so prime square minus z1 prime minus z1 prime square. So in this case, the space-time interval would just be equal to minus of x2 prime minus x1 prime square, which, so it would be negative. And as we've seen, when it's negative, we should define it, a good way to define it is to use delta sigma square. Okay, and so when we use delta sigma square, what we get is this is equal to minus the length of the rod square. So in other words, delta sigma just tells us the length of the rod. Okay, so that's why it was useful to define it like this. Delta sigma just defines the length of the rod in its rest frame. Okay, so delta sigma defines the length of the rod in its rest frame. Or this is what's called the proper length of the rod. So I'm not sure if I defined this correctly earlier. We shouldn't use a c square here. Okay, we just use delta sigma square. in the definition of the space-time interval. Okay, so now let's consider a frame S, which is moving with respect to the frame S prime. So again, let's consider a moving train. So a moving train moving with respect to a platform. So there's a platform S with an observer O here and an observer A over here. And let's consider the rod, okay, on the train. And on the train, the measurements of the rod are occurring at these two spatial locations as seen in the frame S. Okay. However, the events of measuring the endpoints of the rod, which are simultaneous as seen in the frame S prime, that is, S prime describes the coordinates of spacetime coordinates of this point as t1 prime, x1 prime, y1 prime, z1 prime, and the measurement of this coordinate as the same coordinate in time, t1 prime, but a different spatial coordinate, x2 prime, y1 prime, z1 prime. These two events of the measurements of the endpoints of this rod in frame S prime do not appear to be simultaneous to observers on the platform. That is, the observers on the platform will measure a different time t1 and a different time t2 for these space-time points. Okay, and the observer on the ground will also measure some spatial location, let's say x2, and let's say y1, z1. Oops. For notational consistency, let's use x2 here. y2 and z2. And t2 is and the second space-time point where the observer S prime takes a second measurement of the location of the end prime, the end point of the rod, would be t2, x1, y1, and z1. And again, since we're only assuming that the rod is placed along the x-axis and the motion of S prime relative to S is along the x-axis, y2 and z2 would be the same as y1 and z1. Okay. And so in this case, if observer S were to construct the space-time interval between these 2 points, so how are these two space-time points defined? These are the space-time points at which observer S prime is measuring the endpoints of the rod. And so now observer S takes the difference between those two space-time points. They just have different descriptions for those two space-time points. The time intervals, the important point is that the time intervals, or the times at which those measurements are taken, are not the same. So the simultaneous measurement as made by observer S prime is not the same it's not a simultaneous measurement for the observers S. And so if observer S were to construct the quantity t2 minus t1 square minus x2 minus x1 square minus y2 minus y1 square minus z2 minus z1 square, this quantity would be non-zero, this quantity would be non-zero. Okay, these quantities would still be zero, assuming it's oriented along the x-axis. However, the result that observer S gets from constructing this quantity should be exactly the same space-time interval that we had considered earlier. That is, they should get the same minus delta sigma square. Okay, in other words, they should reconstruct exactly the proper length of the rod. Okay, so it's in this sense that proper time, that is the time interval that has elapsed on a static clock, and proper length, that is the length of a rod as measured in its rest frame, these quantities are space-time intervals, And because they are space-time intervals, these quantities are, we say that they are Lorentz invariant quantities. That is, that these quantities are exactly the same as described by all inertial observers. So again, proper times and proper lengths, which are specific cases of spacetime intervals, and all spacetime intervals are Lorentz invariant. All observers agree on the fact that spacetime intervals are exactly the same, where the spacetime interval is defined in a very specific way. So observers might disagree on their choice of coordinates to describe spacetime points. But once they describe the spacetime points, when they construct the interval between those two spacetime points, which is defined this way, y2 minus y1 square minus z2 minus z1 square. Once they construct this spacetime interval between any two spacetime points, all observers will agree on the value of this quantity. Okay? So this will turn out to be a very powerful thing to work with, because now we know a quantity which is a universal word in all dictionaries. All observers agree on the value of this quantity, no matter how they measure the space-time coordinates of any one particular point and any other particular point.